All right. So, chapter two. Chapter two is called probability theory. And although we're going to be dealing with probabilities throughout the rest of the course, this is the only section that I'll call probability. So it gets a little bit confusing because, like I said, we're going to see probabilities for forever now. But this is the only section where we deal with only probabilities explicitly. So um, it can be kind of a tricky section, um, but hopefully it'll be okay. So let's talk about what is probability. So the probability of an outcome, we kind of have a good idea about. Oh yeah, and my little funny, um, probably. Uh, so the probability of an outcome, we understand things like when you flip a coin, there's a 50-50 chance of it being heads or tails. We understand that because there are two possible outcomes and they're equally likely, right? But really what we're talking about is the proportion of times the outcome would occur if we observed the random process an infinite number of times. Okay, so technically that's the definition of a probability, right? And so this is a good place to kind of highlight that all the three P's that we see in this course mean pretty much the same thing. I say pretty much because the percentage is a little bit different, but a probability is a proportion. Okay, and then a proportion, if you multiply it by 100, you get a percentage. Okay, so from here to here, right, a proportion times 100 is a percentage. So that's why it's only approximately equal. But in your mind, right, whenever you see a P, right, a probability or a proportion or a percentage, they're asking for the same thing. And that can be a little bit tricky in the beginning, right? So, but just all those P's mean the same thing. A proportion is a decimal, right? It's a decimal between 0 and 1. And so let's see. Oh, I flubbed it. Okay, so a proportion is between, or maybe I should write it as a sentence. A proportion is a decimal between 0 and 1. Okay. And so, right, we're going to be dealing with decimals, and in math, in our calculations, we will need to use proportions, right? So we'll need to use the decimal version, okay? But then if the question is asking for a percentage, then we would need to convert it back to a percentage. So a proportion is a decimal between 0 and 1. We must use proportions. Oops. Proportions in our calculations. So for example, if it says, 60% something or other, then in our calculations, we have to use 0.60, right? So divide 60 by 100 to get that decimal. So just like to get a percentage, we had to multiply by 100. Of course, to convert a percentage back to a proportion, we have to divide by 100. So that's good to keep in mind, right? And so let's see, what's next? Oh yeah, I started here. Okay. Some terminology I know is not that fun. I'm trying something new today. Weird, right? Where I put the notes down at the bottom, but I keep forgetting that I did that. So I want to go back and keep doing what I've done for 3 years already. Um, okay, so a random process, but I think it'll be better in the end. But a random process is any process that yields a random result. So things like rolling a die, drawing a card, flipping a coin, right? And so what we see is we could look at all the possible outcomes. So rolling a die, there are 6 possible outcomes. Flipping a coin, there are 2 possible outcomes. Drawing a card, there are 52 different outcomes. I had to think a little bit about that one. But each random process has a set of possible outcomes called the sample space. And we're going to denote the sample space by S. And so all possible outcomes, um, the list of all possible outcomes is called the sample space. There, I almost did it again. You don't know that because you can't see where my hand is tending to, but and I can tell. Uh, okay. Oh, there, I did it. That's the first time. Should we do strikes for me? Who am I kidding? This is a recording, so it's just me here talking to myself. But first strike. All right. Swing, bada bada swing. So we're going to use probability notation, which can take some getting used to. But what we do is we use a capital P, and then we have brackets around whatever we want to take the probability of or give the probability of. So if we want the probability of some outcome A, right, then we read this as the probability of A or P of A. So whenever you have something on the outside and it's kind of bumped up against brackets, then those brackets you're going to read as of, right? And so you might have seen something like f of x, right? So function notation, f of x. What about cat of t? I don't know. Right, and so whatever you see on the outside, and then as soon as you see a bracket, you read it as of, and then of the inside. Okay. So I'll keep the f of x here because that's common. The cat one was just for fun. So the P of A, so the probability of A or P of A, as if you want to read it that way, is fine. If we know the context, then we can specify the outcome, right? So a lot of it is context driven, right? And so the probability of heads assumes that we know that we're tossing a coin, and so heads or tails are the possible outcomes, or even P of 2, then we understand that we're probably rolling a die. And the probability of rolling a 2 is 1 in 6 because we assume that this is a fair die and it's not weighted in any way. So then if you have 6 possible outcomes, then the probability of each would be 1 in 6. Let's talk probability facts. And these will be good to know. And I have it here as it is on our formula sheet, but let's talk about these first, and then we'll kind of convert these word statements into what's on the formula sheet. Or if you prefer, you can just have these kind of available. But so probability facts, just like a proportion, because why? Because they're the same, right? Because a probability is a proportion, well, then if a proportion has to be between 0 and 1, then a probability also has to be between 0 and 1. So a probability must be between 0 and 1. Okay, 0 meaning it can never happen, and 1 meaning it happens every time, all the time, every time. Maybe not all the time, every time. The total probability in your sample space has to add to 1. Why? The sample space is the list of all possible outcomes. So if you've given, here is everything that could possibly happen, each with its own probability. Well, if you add those probabilities up, they should add to one. One of those things has to happen if this random event is occurring. So how we denote this in probability notation, if a probability has to be between 0 and 1, then we say that the P of A, where A is just a placeholder for any event that we want, any random event. So P of A is between 0 and 1 inclusive. It's allowed to be 0, it's allowed to be 1. Okay. The probability of S, the probability of the entire sample space, so something in the sample space happening, is 1. Okay. And so we use that fact quite a bit later on. Okay. But for now, we'll just hold off. I'll just grab this whole chunk here, and that's what I was thinking. I was thinking I could delete the pages as I went. Anyways, that's for me to know and you to find out. Okay. Right. So far, I'm not convinced it's more efficient, but that's okay. Takes practice. So some more terminology. It's going to be a lot of terminology here, but two outcomes are disjoint, or if you prefer to call them mutually exclusive, that's fine, but they mean the same thing. So we can use these interchangeably, right? So disjoint equals mutually exclusive, which you might have heard in, in kind of everyday talk, well, not every day, but in kind of, on TV or whatever. Oh, those two things, they can't be mutually exclusive. Are you crazy? Right. And so mutually exclusive, we kind of have some idea of what that means. Well, what it means is that they cannot both happen at the same time, right? There's no overlap in these events, right? And so what we do is we tend to use a Venn diagram. So a Venn diagram is something like this, maybe. So we have event A and event B, or outcome A and outcome B, if you want. Typically, we wrap it up in a box, and that box represents the entire sample space. So those are all the possible things that could happen. And then here we're probably interested in event A or event B, or maybe there's some overlap that they can happen at the same time. So here, this is called a Venn diagram. And for disjoint, maybe I'll preface it with, if A and B are disjoint, then the Venn diagram is going to look like this. So you have A and B. Okay. Meaning they share no outcomes in common, right? So if A happens, then B cannot happen. Okay? And so what does this mean? Right? Or maybe I'm getting ahead of myself, but it means that the probability that A and B happen together is 0, right? And so that's what it means to be disjoint. And so really what we see is the probability that A and B happen together must be 0. And I'm introducing that a little bit early on in the game, but I do find that people struggle with that a lot later on. So I want to introduce it now, and maybe it doesn't make sense, and that's okay. And then I want to bring it up again in a little bit. Okay, so just kind of stew on it, um, because it's kind of a concept that people have a hard time with, and that's okay. So that's why I'm introducing it early. Okay, so that's what it means to be disjoint. It means that these two events cannot happen at the same time. Um, Before I keep going here, let me just move this to a little bit lower because it's kind of unrelated right now. Oh, so much movement. Okay. So, now I lost my train of thought. They can both not happen at the same time. So if you roll a die once, right, only one of those 1, 2, 3, 4, 5, 6 is going to be right side up. We're ignoring the cases where, you know, it falls on the side. No, we don't consider those cases. But if you roll a die once, only one side will result. Will we go along with that? Will turn up. Both kind of a little bit fishy, but anyways, so only one side will result or turn up. Okay, so therefore, are you guys okay with, well, I guess I'm not asking anyone, but it's shorthand for therefore. Usually people have seen it before, but if you haven't, it's really useful. So kind of 3 dots in a triangle means therefore. Therefore, all 6 events are disjoint. Okay, which brings me to my next. Oh, my computer is doing something weird. It's okay. Okay, it went away. So an event is a set of outcomes or collections of outcomes. So all 6 outcomes, I guess I should say, are disjoint. Because an event is a set of outcomes, and you can tell I'm a little bit kind of wishy-washy on it. It'll be obvious from the question what it's talking about. So it's not something that I'm going to grill you on or anything. But an event is a set of outcomes, so a set of possible outcomes. So for example, if I don't care if I roll a 4 or a 6, it just has to be one of those two, then the event that I'm interested in, we can denote by B, capital B. And just as a little side note, usually for some reason, these events or these outcomes, we tend to use well, we definitely use capital letters. I'm not really sure why, but we do. And actually, I do know, but it's not for us. So I'm like, hey, actually, I do. No, so we use capital letters, and we tend to stick to the beginning of the alphabet unless there is some reason to, uh, you know, if you're flipping a coin, or maybe that's a bad. All of these are starting with C: coin, cards, die. They're all at the beginning of the alphabet already. Maybe that's why. No, I don't know. But anyways, so what we can do is we can denote it by some event B. And what we do is we use set notation here. So this curly brackets indicate the set, right? Or it's set notation. But notice that it's just saying that B is the set of 4 and 6, right? And so I don't care if it's either a 4 or a 6, but I have to group them together because those are the two that I'm interested in. Anything else, I'm not interested. Okay. And what we can do is that because 4 and 6 are disjoint, right? You roll a die and it's either a 4 or a 6. It'll never be 4 and 6 if you roll it once. I flipped a coin. Oops. Um, so a 4 and 6, they're disjoint outcomes. So what we can find is the probability of B, right? What's the probability of B? Well, now B has 2 of the 6 possible outcomes, right? And so ultimately we end up at 2 over 6. But the reason for that is because the probability of B is the probability of 4 plus the probability of 6. Okay. And what we could rephrase it as is 4 or 6. Right, the probability, so B is either 4 or 6. We understand that they can't happen at the same time, but they can, one or the other can happen. And so you get 1 over 6 is the probability of 4, and then plus 1 over 6, which is the probability of 6. And when you add those up, because you've got a common denominator, right, you want to make sure that you're following fraction rules. Adding fractions, you have to have a common denominator. And so when you add these up, you get 1 plus 1, which is 2 over 6. Okay. Good. It gets a little bit trickier when events are not disjoint, right? So what happens when events are not disjoint? I'll bring this up here. What? Need another page. Okay. So what happens when 2 or more? We could consider more, but we're only going to be concerned with 2 in this course. But so what happens when 2 events are not disjoint? So if we consider a deck of cards, right? And I don't expect you to be pros at counts or at cards. I always forget what the names of the suits are. I always want to say these are clovers, but I know that's wrong. I've got the diamonds, I've got the hearts. Mm. But anyways, these are face cards. Doesn't matter. But have some broad idea of, okay, so we've got 52 cards, right? We have 4 suits. I know that much. I may not remember the names of the suits, and that's okay. But we have 3 face cards in each suit, right? So we have these kind of core knowledge, this kind of core knowledge. Anyways, so if we have all the possible outcomes, what's this? This is a sample space, or the sample space in this case, right? So if you have a deck of cards, that is your sample space, or this is your sample space. And so we're assuming that each card is equally likely, and knowing that there are 52 cards, right? That means that each card has a 1 in 52 chance of happening. Fair enough. Okay. And so same thing that we did. What's the probability of drawing a diamond? Well, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 diamonds. And so 13 out of 52, that's the probability of drawing a diamond. Great. Okay. What's the probability of drawing a diamond face card? Now it's just 3 out of 52, right? So see how listing the entire sample space can make it a little bit easier to figure out these probabilities. What if I want to know the probability of a face card and a diamond? Uh-oh. Okay. So, or maybe back it up a bit. Back it up a bit. I did face card and a diamond, I guess, already. So maybe don't back it up. Okay, so a face card and a diamond, that's 3 in 52, right? Because it has to be a face card, that's these three, and it has to be diamonds. Okay. Oh yeah, the one I wanted to say was, what's the probability of a face card or a diamond? So now it can be any one of these face cards, or it can be a diamond, any one of these diamonds, not necessarily a face card anymore, right? So now, because these are not disjoint, what you'll find is you can't just add up the cards and then, so add up all the diamonds, 13, and then add up all the face cards, 12, uh, because what you have is you have this overlap, right, in the diamonds and the face cards. You only need to count those once, right? And so if we let F be the event drawing a face card and D be the event of drawing a diamond, okay, then I've got it all set up down here. Dun, dun, dun. Let me just bring it up. Okay. So what we said was we could look at this deck of cards and we can find the probability of F. P of F is 12 over 52 because there are 12 face cards here. The probability of D is 13 over 52. Okay? And so how do we find the probability of F or D, right? And so what happens is, okay, so like we established, right, we can't just add them up and be done with it because we have this overlap. And so we have to subtract the probability of F and D, which we know is 3 over 52 from just looking at the sample space. So one thing you could do, if you have the sample space, you're more than welcome to just count out how many cards satisfy the F or D criteria and then put it over 52 and then be done with it. That's fine. You would find that it's 22 over 52. Okay. Technically, what you're doing is you're saying the probability of F or D is the probability of F plus the probability of D minus the overlap of the probability of F and D. Okay, and so what you find is you get 12 plus 13 minus 3, which is 22 over 52. Okay. Good. And so this is where we get our general addition rule. And maybe I'll make this slightly smaller so it fits on the same page here. Oh. Okay. So the general addition rule for non-disjoint events says that the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. Okay, so you have to always subtract that overlap. So here I'm using A and B as just general placeholders for some events. In this case, we replaced A with F and B with D, Bob with David. Right, and so you'll want to establish those connections, and then as long as you're consistent, then it's fine, right? But we use A and B, or A or B in this case, just as general placeholders. And here's where I want to go back to what I was saying before, that if A and B are disjoint, meaning they can never happen together, what's the probability of them happening together if they can never happen together? It's 0, right? And so the probability of A and B is 0 if A and B are disjoint, okay? And so what happens is Well, then if this is 0 for disjoint events, then you're allowed to just add up those probabilities. And that's why it worked when we did it earlier, right? So that's where we started. But then this is the one, this is the formula that I want you to use, and just kind of throw that initial one to the side, because it's for the special case of the disjoint events. But I'd rather that you started with this one slightly more complicated and then said, no, because it's disjoint, this becomes 0. The probability of A and B becomes 0. So then I'm subtracting 0. Okay. And so what you'll find is that as long as you have 3 of these 4 pieces of information, right? Either the probability of A or B, or the probability of A, or the probability of B, or the probability of A and B, any 3 of those 4 pieces, you can solve for the fourth piece of information, right? And so that's how these problems are going to go, right? You're going to have 3 of the 4, or have solved for 3 of the 4, and then the next question asks you to solve for the 4th one using this formula. Okay, I'm going to pause it here and clean up my notes a little bit. Okay, so while we're still talking about disjoint events, I want to introduce probability distributions. Now, a probability distribution looks like this. It's a table of all the possible disjoint outcomes, and I'll highlight that because it's really important. Okay, so essentially listing the entire sample space up here, right? These are all my possible outcomes, and then the probability of each outcome is listed down here. Notice in this case, right? And so we're talking about, we're rolling, can't remember what the example is. Oh, it's down here. We're rolling 2 dice, and we're looking at the sum of those 2 dice. Now, if we think about a sum of 2, that can only happen in one way, right? And that's with a 1 and a 1, right? If you want a sum of 3, that can happen in 2 ways, right? You could have a 1 and a 2, or what else could you have? A 2 and a 1? I know. Yeah, we have to differentiate between the order. It's only when you have a 1 and a 1, then there's only one way that can happen, right? But for 3, a sum of 3, you can have a 2 and a 1, or you can have a 1 and a 2, and we consider those kind of unique events. And so the sum with the highest probability is 7, right? And so if you're gambling, or if you're the gambling type, then it would probably pay out the least, right? Whereas if you were betting on either 2 or 12, notice how it kind of like drops down, right? So a sum of 7 has the highest probability, and then it's decreasing as we move away in either direction, right? And so the highest sum that we could get is 2 6s, which is 12. And again, the only way that can happen is with a 6 and a 6, and there's only one way that we can get that. Okay, but so I like to use this one because it's got these kind of changing probabilities, and that's interesting. But we also have these outcomes, right? And so what's important with a probability distribution, which is what this is, okay, is it has to follow 3 rules. Okay, so a probability distribution is a list of possible outcomes with corresponding probabilities, and here we go. So number 1 rule is the outcomes listed must be disjoint. So that's the first thing that you're going to check. There cannot be any overlap here, because then how do you talk about the probability of an overlapping event happening? That is not easy, right? And so we have to be talking about disjoint events. So the sum of 2 dice, it can either be 2 or 3 or 4 or 5, but it can't be any of these 2 at the same time. Okay. Each probability has to be between 0 and 1. And that's going back to, well, that's just a probability rule, right? So probabilities and proportions have to be between 0 and 1. So then, of course, these probabilities that I've given also have to be between 0 and 1. And then all the probabilities, because you've listed the entire sample space, right, has to add to 1. So when you add up all these probabilities, they have to add to 1. Okay, good. So I've got a little exercise here for us to work through. Well, so the table below suggests 3 distributions for household income in the United States. Only one is a valid probability distribution. Which one must it be? What's wrong with the other 2? So I want you to take just a moment, pause it here, and try to figure out which one is the right one, just looking at these rules here. Okay, so I'll pause it because otherwise it feels weird. But you pause it too, try it, and then meet me back here. How did it go? Okay, so let's see here. So first thing I want to do is just make sure that these outcomes that are listed up top are in fact disjoint. And it looks like 0 to 24 and then picking up at 25. That's something that you want to keep track of, right? If you're looking at income ranges, there can't be any overlap. So 0 to 24, 25 to 49. Okay, looks good. So all of these are disjoint, and that's good. So check for all of these. Probabilities have to be between 0 and 1. Okay, so what I'm going to do is I've got option A, option B, and option C. And one that's sticking out like a sore thumb here is that I cannot have this negative probability here, right? So negative probabilities are a no-go. Probabilities over 1, no-go. So that means that B is donezo. Okay, so that's not an option. The last thing that we can check is that the probabilities have to add to 1. Now, if I do 0.18, so I've got my trusty calculator here on the side. So 0.18 plus 0.39 plus 0.33 plus 0.16, I get, spaghetti-o, I get 1.06, and that's bad. Hopefully the last one works out, right? Otherwise we're hooped. 0.28 plus 0.27 plus 0.29 plus 0.16. Phew. Sum of 1. So then C must be the valid probability distribution. Okay. And it's in here in the notes. So since C satisfies all the criteria, it is the valid probability distribution. Great. Awesome. Okay. So we can use probability distributions to talk about expected values. Okay, and so let me just grab this here. Sure, just do the whole thing. Why not? Okay. Expected values are really just the means, mostly because it's plural. But so what we've seen with the probability distribution is that the probability of each outcome is not always the same, right? And so we can still find the mean of a variable x, just a placeholder, where the probability of x varies according to the probability distribution. So just like we saw here, maybe this one is a better example, right? Oh, sorry, it's just catching up there. Okay. Um, so here, right, we've got our different probabilities. What's our expected value? I'm not going to do this one because it's too much math, but our expected value is the mean, right? It is the average still, but we can't just add these numbers up and divide them by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We can't just divide them by 11. Hopefully I did that right. Anyways, um, right, because they have different probabilities. So we need to take those probabilities into account. So I have a simpler example for us to work through. Okay. We can find the expected value of x given the following probability distribution. So x here is the sample space for x. So x can either be 0, 1, 2, or 3, and nothing else, right? And so the probability of x, if the probability of x being 0 is 0.2, the probability that x is 1 is 0.4, the probability that x is 2 is 0.1, and the probability that x equals 3 is 0.3. Right? So that's what this is saying. So these all have different probabilities. I'm just going to add, I can check, right? So these are all disjoint outcomes. Great. These probabilities are all between 0 and 1. So that's good. My last check that I'm going to do is just make sure that they add to 1. So 0.2 plus 0.4 plus oops, helps if I type in the right thing, plus 0.1 plus 0.3 is 1. Okay, so the sum equals 1. Good. So what you want to do is to find the mean of x, right, with these different probabilities. Notice the probability of 1 and 3 are a little bit higher than they are for 0 and 2, right? So they're going to be weighted more, right? What we do is we find the expected value of x, and I guess I have it up here. The expected value of x is the sum of x times its probability. So the sum of the outcome times its probability. So 0 times 0.2 plus 1 times 0.4 plus 2 times 0.1 plus 3 times 0.3. Okay, and so that's your expected value of x. What if, so, and this, so we get the expected value of x is 1.5, and maybe I'll just grab, I'll delete that and grab this last little tidbit here, copy. Okay. So we found that the expected value of x, or the mean of x, is 1.5. Okay. Whereas, let's say that I just asked you to find the the average of 0, 1, 2, and 3, right, without these probabilities, right? So now consider the values 0, 1, 2, and 3. What is the mean? Okay. Technically, the mean, just to kind of use some notation from last day, x bar is the mean, which is the sum of x over n. N in this case is 1, 2, 3, 4, right? And so we have 0 plus 1 plus 2 plus 3 over 4, which puts me at 6 over 4, which was a really bad example because they worked out to be the same. But that's not necessarily the case. Sorry, I should have played around with it a little bit more. only the same by fluke. Okay, should have weighted those probabilities a little bit heavier. But so what's going on here? Really what I'm doing is I'm taking, so really what's going on here is I have X, I have a probability distribution, X, 0, 1, 2, and 3. Because I have 4 outcomes, right? The probability here is 1 in 4, 1 in 4, 1 in 4, and 1 in 4. So then when I take the expected value of X is the sum of X times P of X, what happens here? Well, I get 0 times 1 over 4 plus 1 times 1 over 4 plus 2 times 1 over 4 plus 3 times 1 over 4. And because I want to keep it on the same page here, right, this becomes 0 over 4 plus 1 over 4 plus 2 over 4 plus 3 over 4. I've got a common denominator of 4. What can I do if I have a common denominator? It means that I can add these all up, right? Add up the numerators and put them over the common denominator. And I am going to cheat and go across the page here. So that's the same as 0 plus 1 plus 2 plus 3 over that common denominator of 4, which is exactly what we do, right, when we find the mean. But we don't think of it that way, but that is what we're doing, right? We're distributing these probabilities to be the same. And so really, when we talk about finding the expected value, what we're doing is not that different, right? It feels different, but it's not actually different. All we're doing is we're acknowledging that, okay, we're going to have these different probabilities for each of these outcomes. So we need to take that into account. Okay, good. Give me a break here. Okay, so those are expected values, but expected values are just means, right, or averages. So the mean is what we would expect, right? That's the kind of the general, if you had to take a guess at something, you should probably guess that it's going to be the average, right? There's no reason to expect anything else but the average. And so that's why the expected value is the average. So now let's talk about the complement of an event. Oh, fun to say. The complement of an event, whenever I introduce the complement, it makes me think of this really stupid video. Hopefully you've seen it. It's, I think he's German, and he's like, give me compliments. Anyways, it's really funny, and you need a distraction right now. Go look it up, and then come back here. Anyways, the complement of an event is all the outcomes when the event doesn't happen. And so, for example, when we said B is the event of either a 4 or a 6, we understand that, well, 1, 2, 3, or 5 could happen. And that's what we call the complement of B. And so you can denote it by a C, a superscript C, or you can use a prime, and you read it as not B. So B, the complement of B, not B, or if you're using prime notation, it's a little bit weird. If you've taken calculus, it's going to feel weird. So you might not want to do that. Sometimes, context dependent again, and I say that a lot, but it's true. You'll know not to take the derivative of this thing, and you'll know that you mean the complement. And so in general, what we have is, okay, so these are the outcomes in the complement of B, 1, 2, 3, 5, right? In general, if I wanted to find the probability of the complement, well, if I told you that the probability of a 4 or a 6 is 2 and 6, what's the probability of not a 4 or a 6? Well, that's the probability of the complement, right? Which is going to be the probability 4 over 6, right? Add to 6 minus 2, hard math, right? Um, right. And so in general, we say that the probability of the complement of A is just 1 minus the probability of A. And we already introduced this briefly when I was arguing that we shouldn't use pie charts because they're really only obvious if you only have two possible uh, slices. But then you could just say, well, if you know how many yeses there are, then you also know how many no's there are, right? And so you only need to report one of those numbers, and then everyone has a good understanding of the complement, right? And then the complement um, is the opposite, right? Okay. Let me just, sorry, clean up here. Okay. So, little office humor. Third time's the charm, false. Each time has an equal probability of being the charm. So what we're talking about here are independent events, right? And so here, what we're referring to are called independent events. Okay, so independent events, two events or outcomes, and we kind of use them interchangeably, even though they're not interchangeable necessarily, but they have the same properties. So two events or outcomes are independent if knowing the outcome of one does not affect the probability of the other. So notice that we're talking about the probability, right? Whereas before we were talking about, when we were talking about disjoint, we were asking, well, can these two things happen at the same time or not? Right now we're talking about, okay, so independence has to do with, okay, if knowing that something has happened, so if I know that it was a heat wave yesterday, what's the probability of it being a heat wave today? I mentioned that because heat wave, and it's insane. But anyways, so anyways, so knowing that there was a heat wave yesterday, what's the probability of a heat wave today? Well, it's higher, right? Because we had one yesterday. If it snowed yesterday, the probability that it'll snow today is higher than if it didn't, right? And so we call those dependent events, right? Because knowing the outcome of one affects the probability of another. Uh, So independent events are things like when you flip a coin or you roll a die, and people really get caught up on confusing independent events for dependent events, right? So, uh, well, now I'm just failing to find an example. A lot of them are gambling related, but I want to kind of stay away from. But so when you flip a coin, right, it doesn't matter if you've had 14 heads in a row. The probability that you get another head is still 0.5. The probability of getting that many heads in a row is very, very low. And so that's what you're thinking of when you're going, oh no, it has to be tails. It has to be tails. But each time you flip the coin, it's independent of what happened before, right? And so it's hard to shake that, right? But that's an important concept, right? So when you flip a coin, each outcome is independent of the next outcome or the previous outcome. Same thing with rolling a die, right? If you roll a die, it doesn't matter that you've had 4 ones in a row. You could still get a 1 with a 1 in 6 probability, right? And so two events or outcomes are not independent if knowing the result of one affects the probability of the other. So for example, if we're talking about stocks or weather, disease, right? If you've been in contact with someone with a disease, or sorry, a contagious disease, then yeah, you're more likely to have that disease. Okay. Um, Even drawing cards without replacement. Now, if you're drawing cards, so you've got your deck of cards here and you're pulling out a card and then you're putting it back in the deck, well, then the probability of the cards stay the same, right? As long as you're replacing them, you still have 52 cards in the deck. Nothing's changing every time. And so that would be independent, right? Each draw would be independent because you're replacing it. But when you don't put it back, right, knowing that I've already pulled um, 3 red cards, for example, well, that affects the probability of another red card, right? Because now I know that there are fewer red cards in the deck than I had in the beginning, right? And so the probability of another red is smaller than or less than in the beginning, right? And so without replacement, then you have dependent events. So if A and B are independent, okay, and I'm going to highlight this here, kind of typeset all smushed, but that's okay. So if A and B are independent, the probability of A and B is going to be the probability of A times the probability of B. And what I want to do is I just want to highlight here, this is super important because as soon as I introduce this, people tend to latch onto it, and that's the only thing that they think they can use to find the probability of A and B. But there are a lot of cases where A and B are not independent, which means we can't use this formula, and that's what we'll introduce in the next section. But for now, right, how I want you to use this formula mostly is, unless it says, okay, A and B are independent, then fine, go ahead and use this formula if you need to find the probability of A and B. But what we do is we can use this property to determine if A and B are independent, as long as you have the probability of A and B, the probability of A and the probability of B, right? Because then what you can do is you can multiply the probability of A times the probability of B, and if they multiply to something different than the probability of A and B, then they're not independent, right? And they have to be exactly the same for them to be independent. Okay, good. So here, let's do an example. Add a page. Okay. So I want to use this example to work through some of these things that we've introduced, some of these ideas. So in a math class of 30 students, 17 are boys and 13 are girls. On a unit test, 4 boys and 5 girls made an A grade. What a weird way to say that, but oh well, I just copy blindly. And I've used this so many times, and the wording irks me every time, but then I can't think of a better way to phrase it, so I guess it's on me. If a student is chosen at random from the class, what's the probability of choosing a girl, choosing an A student, choosing a girl who got an A on the test, okay, choosing a girl or an A student? Remember, there were boys that got A's too. And then finally, are choosing a girl and choosing an A student independent? Okay, so we're going to work through these problems. I find that the easiest way to attack these is by setting up a Venn diagram. Now, this Venn diagram, we're talking about the main events that we're talking about is it seems to be a girl and an A. Okay, and so what I want to do is I'm going to set up this Venn diagram. Okay, and you don't need the Venn diagram. I just find that it's helpful, so I'm gonna show you how to use it to help you solve these problems. And so I find a Venn diagram is helpful when solving these types of problems. When solving these types of problems. Okay. So remember, our Venn diagram looks like this. And so I'm going to have my girl circle and my A student circle. Notice that I've made them overlap. What's this overlap about? They're all the girls that got A's, right? There were girls that didn't get A's, right? And there were A's students that aren't girls, right? And so anything outside this G circle, well, that makes a boy, right? And so, and then anything outside this A circle, that makes not an A student. Okay. And so what we can do is, and Venn diagrams are useful and tricky at the same time, in that we can either do counts in here or you can do probabilities. I'm going to do counts for now, just to kind of show you the ropes. And then you can think about the probabilities as well. So if you have 30 students in total, then the area outside the G circle has to be 17, and 13 are girls, which means temporarily I'm going to put 13 as this G circle. Okay, and I'll show you why it's temporary in a little bit. Well, it's because we've got this little chunk that's a little bit special. It's still part of the 13, right? So let's see where we're at here. On a unit test, 4 boys and 5 girls got an A. Okay, so 4 boys and 5 girls. So these are the 5 girls who got an A. Okay. And then these are the 4 boys who got an A. And this area is just this half circle. Notice that the sum inside the A circle here is 9, meaning that 9 students in total got an A. Okay, and so this is why this 13 is temporary, is because, and maybe I should have used, let me switch colors here. Four. Okay. And so here, 4 boys got an A. Okay. Which means what? 13 minus 5 girls. 13 minus 5 is 8. So 8. And I'll often do that. I'll kind of jot down things as they show up in the question, just so I don't miss anything, but then I'll change it. And maybe that's confusing. Maybe I shouldn't have done that, but nah, you've got this. So here, 8 girls did not get an A. Okay. So now we've got 8 girls who didn't get an A, 5 girls that did get an A, and 4 boys who got an A. Who's missing? The boys that didn't get an A, right? A boy is outside the girl circle, and if they didn't get an A, they're also outside the A circle. So out here, kind of, we have how many 17 are boys, but 4 of them are already taken care of here. 13. 13 boys did not get an A. Right? Sure, yeah. So what you can do, because we know that we need a total of 30 students, right? Because that's what the question says, in a math class of 30 students. Okay, so what we have is we have all these different areas. And what I'm going to do is I'm going to do the same half circle here for the blue. Okay, good. And so you want to add these up and make sure that they add to 30. So we've got 8 plus 5 plus 4 plus 13, right? Just make sure that all those puzzle pieces fit together to make 30, and they do. Okay, so that's good. So knowing that there's a total of 30 here, what's the probability? Now we can start to answer some of these questions, right? And so what's the probability of choosing a girl? So the probability of a girl, well, that's everything in the G circle. We've split them up because later we're going to be interested in the A students or the G, right? And so, but overall, there are 13 girls out of 30, right? And so 8 plus 5, but I'm just going to go straight to 13 out of 30, mostly because it was in the question. What's the probability of an A student? Now, looking at this Venn diagram, right? The probability of being in the A circle is 5 plus 4 out of 30. So 9 out of 30. And the probability of A is 9 out of 30. Good. Okay, doing well. So we put a lot of work into making the Venn diagram, and then the rest of the problems are quite easy because then we can just use the Venn diagram to answer the questions. So what's the probability of choosing a girl who got an A on the test? So looking here, right, there are only 5 girls who got an A on the test. And also notice you could have grabbed all this information from the blurb, but I just want to give you some different tools that you can work with, and the Venn diagram I find works really well. So, but if you don't need the Venn diagram, you don't have to. It's not a must, but I find it helpful. So the probability of choosing a girl who got an A on the test is 5 out of 30. How do we denote girl who got an A on the test? That's the same as the probability of G and A. Right? Because they have to be a girl and they have to get an A on the test. And so is going to be 5 out of 30. What if we want to know what love is? Okay. What's the probability of choosing a girl or an A student? Okay. A couple of ways we could go about this, right? And so we can solve this in 2 ways. We can solve this in 2 ways. Option 1, using the Venn diagram. Okay. So they have to be a girl or an A student, which means they can either be in the G circle, so 8 plus 5, or they can be in the A circle, but you don't want to count this 5 twice, right? We've seen that already. We've seen that in action, right? And so you only want to count this 5 once, right? So it's going to be 8 plus 5 plus 4 because they can be in the A circle as well. So the probability of G or A is kind of anything that satisfies either of those criteria. So it's either 8 plus 5 plus 4 over 30. So the probability of G or A is 8 plus 5 plus 4 over 30. 8 plus 5 plus 4 makes 17 out of 30. And I'm going to keep it as a fraction just because it's a lot easier. And often we prefer to report them as exact values, so as fractions. So it doesn't hurt to practice. Option 2 is using the formula. What formula? Hey, it wasn't that long ago. Remember the formula, the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. Oh, that one. Right. So a little bit sneaky. Okay, so kind of weird because I'll replace A with G and B with A. Oh, stay with me, folks. So the probability of G or A is the probability of G plus the probability of A minus the probability of G and A, right, in our case. So notice how I just kind of mapped from these placeholder A's and B's to my question G or A. Okay. I have all these pieces of information from the previous questions, right? And so that's where it was kind of leading us down the road of, okay, so now you have 3 of the 4 components. Can you use this formula to find the 4th component? Okay, so then from before, the probability of G or A, the probability of G was 13 over 30. The probability of A was 9 over 30. So I'll start there. 13 over 30 plus 9 over 30. Let me clean that up. Minus the probability of G and A, we already decided was 5 over 30. Notice that these are all over a common denominator, so that's good. So we can combine these and say 13 plus 9 minus 5 over 30, putting me at 13 plus 9 minus 5 is indeed 17 over 30. Okay, so none of these required a Venn diagram. I just want to make that clear because often I'll get these frantic texts from people saying, I didn't need a Venn diagram. Is that really bad? Or no, that's totally fine. You don't need to use a Venn diagram. They're just tools to help you solve these problems or kind of map out these problems at least. Okay, good. Last thing we want to answer is whether these 2 events are independent or not. How do we know if choosing a girl and choosing an A student are independent of each other? And what does it mean to be independent? It means that knowing that you picked a girl out of the crowd, does that affect the probability of them being an A student, or vice versa? Does knowing that you have an A student affect the probability of it being a girl that you have in your hand? This miniature person, I guess in my mind. Right, and so remember what we said, if A and B are independent, then the probability of A and B is the probability of A times the probability of B. In our case, therefore, G and A are independent if the probability of G and A, which we know is 5/30, right, from before, is equal to the probability of G times the probability of A. So 5/30, I want to try to keep it on the same page here. The probability of G was 13/30 and the probability of A was 9/30. So 13/30 times 9/30. Multiplying probabilities, right? I am going to convert these to decimals because otherwise I have a hard time comparing them if they're not reduced. So 5 divided by 30 is roughly 0.1666 repeating. And then 13/30 times, I'm just going to do it in one, going to go here, times 9/30 using brackets puts me at 0.13. These two are not the same, right? So because these two are not the same, so G and A are independent if they're the same, but since they're not the same, G and A are not independent. So therefore, G and A are not independent events. What does that mean? It means that knowing that you have an A student, it means it affects the probability that it is a girl, okay? Which leads us to conditional probabilities. But I need to have some water. Okay. So conditional probabilities are when you do not have independent events, then how are you supposed to find the probability of A and B if this is only true for independent events? And what we've noticed is that we're going to have a lot of dependent events on our hands, right? And so we need some way to deal with that. So before we introduce that, let's talk about conditional probabilities. And so we usually have information in a table like this. It's called a contingency table, which briefly introduced in the last video. But so here we have a sample of 792 teens. And so our total sample size is down here in the right-hand corner. And so the college variable means that the teen went to college immediately after high school. So even if they took a year off, it's a no college, right? Even if they did eventually go to college. But so we need to be really kind of clear on the criteria here. And so the teen went to college immediately after high school. The degree variable, right? So they either went to college or they didn't, right? The degree variable is whether at least one parent of the teenager completed a college degree. And so if that's true, then it's yes for the degree, or if that's not true, then no degree, right? At least one parent. And so there are some kids who have at least one parent with a degree who went to college immediately. And there are some kids that went to college immediately, but they don't have a parent with a degree, right? And so the total number of teens that went to college immediately after high school is 445 out of 792, right? So we can use this table to extract a lot of probabilities. And so we are letting D be representative of at least one parent has a college degree. It's a lot easier to write D instead of writing out these explanations every time, right? But if you're going to use some shorthand notation like this, then you have to tell me what it is. As long as you've told me what it is that you're saying and kind of using as abbreviations or notations, then it's fine, right? So let D be at least one parent has a college degree, and C be that the teen went to college immediately after high school. So now we're going to answer some of these questions here. What proportion, and I just want to highlight here, which is a probability, which is roughly a percentage. The reason I highlight that is because this question could have just as well said, what percentage of teens have at least one parent with a college degree, right? What is the probability of a teen with at least one parent with a college degree, right? And so these three P's are used interchangeably in a question, and you just have to kind of be clear on which one you should be reporting, right? If it's a percentage, you would have to multiply by 100. So what proportion of teens have at least one parent with a college degree? I think I have these already worked out. So let's just read these problems. Given that at least one parent completed a college degree, what's the probability that the teen went to college right after high school? Okay, so now we've got this conditional probability because it says given that at least one parent. So now you know that at least one parent completed a college degree. So you know that now all of a sudden you're taking it out of a total of 280 teens, right? Instead of the full 792. Right, so it's conditional on, okay, so you know that at least one parent has a degree, putting you, there's only 280 of those teens, right? And so what's the probability that the teen went to college right after high school? So then the probability of C given D, okay, is, so the probability that they went to college immediately, given that they have at least one parent with a degree, is 231 over 280. Okay. And so that's going to be a conditional probability. When we don't talk about the overall 792, it's going to be conditional on some criteria. Let's read this third question before we go any further. So given that a teen is randomly selected and she did not attend college right after high school, so now we know that they didn't, so it's the complement of C, okay, is basically what it's saying. What's the probability that at least one of the parents has a college degree? So now we want to find the probability of D given that they did not go to college. Well, that's going to be 49 out of 347. So these probabilities, we can extract them from this table. And if you take your time, it's not that bad. It's not that bad. Okay. Or we can use a formula. But I didn't want to spring the formula on you until we had established that you could find it just using the tables. So we can find these conditional probabilities using the contingency table or by applying this formula. Okay. And so here, this vertical bar, you read as given. Oops. So the probability of A given B is the probability of A and B divided by the probability of B. Or depending on what you want to solve for, right? Remember, we're trying to figure out a replacement for the probability of A and B is the probability of A times the probability of B. That's only true if A and B are independent, right? And so now we're trying to find a replacement so we can rearrange, we can multiply both sides by the probability of B, move that over to the left here. Revolving door around the equal sign here, and you get the probability of A and B is the conditional probability. So P of A given B times the probability of B. Okay. And so this gives us the general multiplication rule for events that are not independent. Okay. And I just want to highlight here, right? These are conditional probabilities. Okay. As soon as you see given, and that's reflected here in the formula, the probability of A given B. So we can use the general multiplication rule for events that are not independent. Notice too, right? Notice if A and B are independent, what's the definition of being independent? It means that the probability of A does not change knowing B or not knowing B, right? Or I should say knowing B, right? And the probability B doesn't change knowing A. And so then the probability of A given B is just the probability of A. Uh-oh. It's all starting to come together. Because then what can we do here? The probability of A and B, the probability of A given B if A and B are independent, right? I'm taking you back to that independent case. Well, if they're independent, the probability of A given B, it doesn't care about B. So then the probability of A just is the probability of A. So then, so the probability of A and B is the probability of A times the probability of B, right? Because the probability of A given B is replaced by just the probability of A if A and B are independent. So this is the one that I want you to use every time, right? And if they're independent, then you can say, okay, well, then the probability of A given B is just the probability of A because it doesn't matter. It's not conditional. So again, I got smushed here. So marginal probabilities, maybe I'll copy and put this on a separate page so it's a little bit more clear that they're separate. Okay. But now I put it, anyways. Put them on the same page to save some space here, but that's okay. Marginal probabilities, so now just some quick definitions, are probabilities based on the single variable without regard for any of the other variables, which are really just going to translate to the margins of the contingency table, right? So if you need the probability of C, oh, sorry, let it catch up here. The probability of C, well, that's going to be 445 over 792, right? What's the probability of the complement of C? Well, it's going to be 347 over 792. Or what else could we do? 1 minus 445 over 792, right? Which is going to be 347 over 792. Right. So these, we can find the marginal probabilities, and that's just, there's no regard for the other variable, right? So if you're over here in the rows, in this case, we're talking about college and not college, or in the columns, we're talking about degree or not degree or no degree. Joint probabilities are all the probabilities in the body of the table. So if you think about the body of the table and the contingency table, then those are the joint probabilities. If you kind of talk your way through it, 231 is what? There were 231 teens that went to college right away after high school and have at least one parent with a degree at home. So that's why it's a joint probability. And what's the probability of C and D? Well, it's 231 over 792, right? So we can talk about the joint probabilities, which is just all the probabilities in the body of the table. So usually what we do is we can rewrite the contingency table as a probability table. And so you'll also notice that the joint probabilities we just defined, right, are at the body of the table, and they're going to add to their respective marginal probabilities. And then eventually in the very bottom right hand corner, they'll add to 1. Okay. So we can find, let me just delete this here. Delete, add a page. Oh, I almost deleted. I don't know how to undo. Can I shake this thing like I do my phone or what? Okay, so the conditional probability or the probability table here. Now we've converted all of these to probabilities by dividing each number by 792. So you always want to divide by the overall sample size. There are other things, it depends on what you want to find, right? But for this probability table, you just want to divide everything by 792. So now it's easier to see the probability that they didn't go to college immediately and not having at least one parent with a college degree at home is 0.38, right? And so we can read this a lot easier than taking some fraction over 792. So I always like to start here, and now I'm ready to answer these questions. Okay. And so let's go ahead and look at those problems that we had here. Copy, and hopefully, I didn't want that. And this, it's not going to delete. How do I? Oh, well, okay. We carry on. What proportion of teens have at least one parent with a college degree, right? So here, and maybe I'll do these kind of step by step. What's this asking? Sometimes the hardest part is converting it into probability notation so that we can use all our formulas. The probability, because a proportion is a probability. So what proportion of teens have at least one parent with a college degree? So we want to know, oh, sorry, D. Have at least one parent with a college degree. That's D. So the probability of D, now that we've converted all these to probabilities already, it's really easy to find, right? Because regardless of if they went to college or didn't, overall 0.35 have at least one parent with a college degree. So 0.35. So first, and maybe try this question, try writing it out in probability notation. Give it a little pause here and try it out. but I'm impatient. So here we go. Um, Given at least one parent completed a college degree. So given D, right? So here, I'll make this a kind of a multi-step process, even though you don't have to. So it really says, given D, what is the probability of C, right? That's what it's actually asking. And so I can I can rewrite this in probability notation and really say, find the probability of C given D. Yeah. And from the formula, right, we know that the probability of C given D is the probability of C and D divided by the probability of D. All of a sudden, it's not so bad, right? It's the probability of C and D, which we can find, right? And from the probability table, the probability of C and D is 0.29. And the overall probability of D is 0.35. So 0.29 over 0.35. Yeah. Which, let's see if it kind of simplifies to anything kind of nice. Probably not. It simplifies to 0.822857142886. That's the probability that the teen goes to college immediately, given that at least one parent has a college degree, right? Quite a bit higher. Okay. Oh, we had one more I wanted to do, but yeah. Paste, crop, bink. So now, given that a teen is randomly selected and we find out that she did not attend college right after high school, what's the probability that at least one of the parents has a college degree? Okay, so again, try to write this out in probability notation and maybe even solving it. But writing it out in probability notation is the hardest. So I'll give you a little time to pause it. Welcome back. Okay. I guess I didn't need to give a pause, but anyways, I just don't want you to be scrambling. So now the probability notation that we'll have here is going to be the probability of, so this is what we're given, right? So that's the second part that we know, but we want to find the probability that at least one of the parents has a college degree. So the probability of D, given that a teen is randomly selected and she did not go to college right after high school, we denote that by the complement of C, right? Again, these conditional probabilities, right? When we have this bar in here, the given, that's a conditional probability. How we find it is the probability of D and the complement of C over just the complement of C. So it's the probability of D and the complement of C divided by the probability of the complement of C. And we have these probabilities, we can just use the table. Okay. The probability of D and not C is 0.06 divided by the probability of not C is 0.44. Right, so 0.06 over 0.44. .06 divided by 0.44 is roughly 0.13636. It seems to be repeating. One thing that I will point out is that this table is using rounded values. So if you were doing these questions, and like I showed you earlier, right, we could have answered all these questions, or all of them, all three questions, just using this table, right? For example, when we said, given at least one parent completed a college degree, what did we do? We said, okay, so now I have to be in this D column. So now my total is out of 280 instead of 792. So given that information, what's the probability that the teen went to college right after high school? So the probability of C given D is 231 over 280. Now, if I compare 231 over 280, it's 0.825, right? That's sort of close to what we found here, but the difference is because these are using rounded values, right? And so here I'll add in versus 231 over 280 using the table. Oh, I'll bump this down here, which is 0.825, right? And so these are rounded values. So that's why we get slightly different numbers, but either way that you want to answer these problems, I'm okay with either way, right? But I do expect you to know this formula and know how to use it, right? But it might be good to practice either way, right? Solving these problems using that original table, the contingency table, or using the formulas and the probability table. Okay, good. So I think this is the example I just did. Which is good, I guess. But I'll just keep it in here so I don't cut anything out. It's the exact same thing that we went through. So, or if we use the probability table, we get slightly different answers due to rounding. And so it's exactly what I said. It all checks out. All right. Good. So the last thing I want to introduce is, unfortunately, also the most important thing and the hardest thing. Very unfortunate, right? And it is on tree diagrams. And I can delete this. And put this in here. Tree diagrams are very important. Okay. We commonly have to deal with consecutive events. So, for example, you write a midterm and then you write a final exam, right? You flip a coin and then you flip the coin again. You flip the coin again, you flip the coin again, for example, right? You draw a card and then you don't replace it in the deck, right? What's the probability? So what can happen next? And so when we have these consecutive events, a tree diagram can be really helpful. At least as long as it's not like there are so many different outcomes at each step, then it becomes kind of out of control. But for these problems, right, as soon as you read a question where you have these consecutive events, or even if you could convince yourself that they could be consecutive events, then a tree diagram might be helpful, right? And like I said before, you don't need to use a tree diagram, but it certainly makes it so much easier to look at the problem and try to figure out where you need to go. Um, so there are lots of different problems that we could solve with a tree diagram. So it's easier if we just do an example. So here's the example. 13% of students earned an A on the midterm. Of those students, okay, so of those 13, so not 47% overall, but 47% of the 13 got an A on the final. Okay. 11% did not get an A on the midterm, but got an A on the final, right? And so there are all these different options, right? You can get an A on the midterm or you don't. You could get an A on the final or you don't. But even if you didn't get an A on the midterm, you could still get an A on the final or not, right? And so you can see this tree building. And the first layer, I like to think of it as, is the midterm. And then the second event is the second layer, and that's the final exam. And they'll each branch will have a probability. And so we're going to build a tree diagram labeling all the appropriate probabilities. Okay. So let's see here. Maybe what I'll do is I'll copy this and maybe shorten this a little bit so I don't have it so all over the place. Okay, so my first layer here is the midterm layer. That's the first thing that happened. And imagine here, you're standing here and you either get an A or you do not, right? So here, because I know this problem, and you would get there pretty quickly. It gets confusing because you're talking about an A on the midterm and an A on the final, so you can't really use A. But what I'm going to do is I'm going to use M for an A on the midterm and F for an A on the final. And I know that sounds weird, but it's kind of the cleanest way to go. And so what I'm going to do here is I'm going to define those, and then I can use them. Let M be an A on the midterm. And ironically, F is an A on the final. Okay. So the midterm layer, you can either go down this M path or the complement of M, not M. Okay. We're given the probability of going down this path, right? An A on the midterm, 0.13. Remember what I said for calculations, we can't use the percentage, we have to use the proportion, right? So we have to use 0.13. Which means what? It means that we know the complement of M is 1 minus 0.13. So 1 minus 0.13 is 0.87. Oops. What's important is that the sum of the probabilities in each layer has to be 1. So we can't leave an option out here. We have to consider all the different outcomes. Usually there's only 2 or 3. So in this case, there's only 2. Get an A or you don't. So then we move on to the final exam layer. All right. So now each of these outcomes get a branch, right? And I'll shorten this one up a little bit. There. So you either get an A on the final or you do not. Or you get an A on the final, oops, sorry. Or you do not. Okay. We've been given conditional probabilities, right? So 13% of students earned an A on the midterm, and of those, 47% got an A on the final. So if you're down this branch, then the probability of an F here is 0.47. 0.47, which means what? Means that the probability of heading down this A on the midterm and not getting an A on the final is 1 minus 0.47, which is 0.53. Okay. I said they have to add to 1, and I'll show you what I mean by adding to 1 in the second layer. It's really down here that it has to add to 1, but I'll show you, because these are conditional probabilities. 11% did not get an A on the midterm, but got an A on the final, right? So they didn't get an A on the midterm, but they did get an A on the final. And it's not exactly clear to me, but I am going to go ahead and assume that it's 0.11 here. So I am assuming that this is given information, right? So given that 11% did not get an A on, no, sorry. How is it conditional? I'm assuming that they didn't get an A on the midterm, but they got an A on the final. So of those who did not get an A on the midterm, 11% got an A on the final. So I'm going to rephrase this. Of those who did not get an A on the midterm, 11% got an A on the final. That's better. That reads more cleanly. And that's what I wanted it to be anyways. Which means the probability of not getting an A on the midterm and not getting an A on the final, or not getting an A on the final given that they didn't get an A on the midterm, yikes. 1 minus 0.11, that's all I'm trying to say, is 0.89. Okay. So what we can do is we can find the probabilities of ending up at the end of each of these paths, right? And so at the end of this path here, I have an A on the midterm and an A on the final, right? And so what I like to do is I like to do MF, which is really just shorthand for M and F, or rather, the probability of M and F is 0.13 times 0.47. So what I can do is I can multiply down each of these branches and find the probability of M and F, the probability of M and not F, the probability of not M and F, and the probability of not M and not F. So kind of multi-step process here. First, I want to just go through and indicate what events have happened at the end of each path, because that's going to help me highlight some instances that I'm interested in. So here, not M and F, and not M, not F. And then what I can do is I can find the probabilities at the end of each of these, just like this, right? So if I multiply down the branches, and this is true even if the midterm and the final exam were not dependent. So if we had independent events, then we can still multiply down these branches, right? But if they're independent, then you wouldn't have these conditional probabilities, but it still works the same way. So, and it's a little bit easier, because then if the probability of getting an A is 0.13 throughout, then it would be 0.13, 0.13, 0.87, 0.87, 0.13, 0.87, right? And so it's a lot easier if you have independent events. In this case, we do not. We have dependent events. So what we're going to do is we're going to go through and just find the probability of M and not F is 0.13 times 0.53. And then kind of go down here. I always run out of room. The probability of not M and F is 0.87 times 0.11. And the probability of not M and not F is 0.87 times 0.89. Okay. Which, if I do these calculations, right, I get 0.13 times 0.47, and I'm going to pause here and do these multiplications and jot them down so you can do the same. Okay, so I found each of these probabilities, and this is the highest probability for sure. And as a check, the sum of these probabilities at the end of all the paths, right? Because we've considered all the possible outcomes, well, the sum of these probabilities has to be 1, right? And so 0.0611 plus 0.0689 plus 0.0957 plus 0.7743 does equal 1. So that's good. Gets a little check mark, right? Because these are all the possible outcomes. All possible outcomes. So the total probability has to be 1. So that's kind of cool. Let's see. That's what we wanted to do. So build a tree diagram labeling all the appropriate probabilities. It's a lot of work, but once you have the tree diagram, you can answer a lot of these questions fairly easily. So let's go ahead and have a look at what are these questions. What's the probability of a student earning an A on both the midterm and the final? Well, we already found that probability. So all we need to do is convert this statement into probability notation, and then we can pull it from the tree. Or if you prefer, the probability of a student earning an A on both the midterm and the final. So they have to go down this M branch and they have to go down this F branch, right? And so the total probability here is 0.0611. So the probability of M and F is 0.0611. Okay, good. And if you've shown your work in the tree, then you can just make the statement like we just did, right? Just pulling it from the tree because you've already shown how you found it. What is the probability of a student earning at least 1 A on either the midterm or the final? Okay, so what I want to do is I just want to look at, and without kind of messing with this beautiful tree that we've made, I'm going to replicate this just briefly here. And I am going to cheat because I can. And why not cheat all the way here? Copy. Paste. Okay. I'm going to clean this up a little bit here. Okay, let me pause and clean this up. Okay, So usually what I do, and it's bad, but because I do it, you're allowed to do it too. Usually what I do is I list the outcomes, MF, M not F, and then I just jot down the probabilities underneath. I don't use the probability notation, right? I know it's there and it should be there, but you're allowed to do it because I do it and I know it's bad. And as long as you know it's bad, then it's okay, right? That's how it goes. Okay, so what's the probability of a student earning at least one A on either the midterm or the final? So let's just take a walk on the wild side here. So here, that's this branch because it's an A on the midterm and an A on the final. So that's at least one A. As long as you got an A on the midterm, you can get not an A on the final and still have at least one A. If you get not an A on the midterm, then as long as you get an A on the final, then you have at least one A. Okay? And so the probability of at least one A is going to be this or this or this branch, right? The only one that it doesn't include is this last branch, right? So there are a couple of, or yeah, a couple as in two. You can probably think of more, but two ways that we could easily solve this problem. And it depends on how your brain works and how you want to approach this, right? But we also established that the total probability here is 1, right? So if I want all these probabilities except this one, I could just do 1 minus 0.7743. And that's a trick that we'll use a lot, right? Using basically the complement of at least 1. So there are two ways. There are two ways to solve this. The first one is that the probability of at least one A is the same as the probability of M and F, or, oh, I'm gonna bump it down and try to keep it on the same page here, but I wrote too lofty, or the probability of M and not F, or the probability of not M and, I should write the word and F. There, that's proper. Side note, when you see the word and is multiplication. And that's like broad strokes, but it works 50% of the time, it works every time. But and is going to mean multiplication, whereas or is addition. So when you catch yourself saying this, it could be this branch or this branch or this branch, right? Then you would add up those probabilities. But to get down each branch, you would have to go get an A on the midterm and an A on the final to end up at the end of this branch, right? You would have to get an A on the midterm and not an A on the final to end up at this branch, at the end of this branch, right? And so that's how and or tie in. And kind of extra side note, we could use this notation. So an upside down U is the intersection, which is and. So you could use this notation, which is an upside down U. And how I remember it is I just draw an imaginary line here and make it a big kind of round looking A, right, for and. Or you can use an actual U for the union, which is representing or. So you might see that, and so that's why I want it pointed out. But let's get back to our problem here. So the probability of M and F or, so really what we've got is we have the probability of M and F is 0.611, or, which is plus, M and not F is 0.0689, or, which is plus 0.0957. Okay, so if I add these up quickly here, 0.0611 plus 0.0689 plus 0.0957, I get 0.2257. Or option number 2 says that the probability of at least one A is 1 minus the probability of no A's, which is 1 minus 0.7743. And where can I bump this up one line so I can keep it all on the same page for this question here? 1 minus 0.7743 is again 0.2257. So it doesn't matter which method you use. But there will be times when this method will be a lot easier, right? Imagine that you ended up with maybe 8 branches at the end, not just 4. Uh-oh. You'd have to add up 7 instead of just taking 1 minus the last one, right? But it takes a little bit of work to recognize that you can use that trick of, okay, well, they have to add to 1. So what if I just take away this one that doesn't satisfy it, right, for the complement? Okay. Oh. Reset. Copy. Okay, I'm going to pause this, clean this up. Okay, I got it all cleaned up and we're ready for the last question here. So we want to know, what's the probability of a student earning an A on the final, but not on the midterm? Okay, so if they got an A on the final, well, we have 2 branches where that can happen, but not on the midterm. Well, there's only one way that that can happen, and that happens with a probability of 0.0957. So the probability of not M and F, we know from the question before, is 0.0957. Okay. There are a lot of other problems that you could solve with this, right? You could find what's the probability that they got an A on the final? Okay, so I'm going to add that here. Question 5. What is the probability of an A on the final? Okay. That's just, what's the probability of F? Okay. Feels weird, right? So if we kind of go back to our tree here, and let me just copy this clean version. Paste. And we're not talking about these anymore. we get an A on the final here and here. So I'm just going to highlight those branches that get me there. Right? So it can be this branch or this branch. So again, I'm going to be adding these up. So that's the same as the probability of, and maybe I'll put this down here. Makes more sense. The probability of M and F plus the probability of not M and F, which is 0.0611 plus 0.0957. Nice. Okay, so I do want to point out that these formulas are on your formula sheet, but it's hard because if I had just introduced the formula sheet right away, this would have been just, I think some of you would have stopped watching. And that's totally, totally fair. Okay, but we have these probability rules, right? A probability has to be between 0 and 1. The total probability of all possible outcomes has to be 1. The probability of the complement of A is 1 minus the probability of A. All of a sudden, these aren't that bad anymore, right? But we had to get there. The probability of A or B is the probability of A plus the probability of B minus the probability of A and B, right? The probability of A given B is the probability of A and B over the probability of B. Or you can rearrange that here. The probability of A and B is the conditional probability of A given B times the probability of B. And if A and B are independent, notice that it clarifies, right? They have to be independent. Then this is true, right? The probability of A and B is the probability of A times the probability of B. But you can't use it unless that's the case. Okay. The very last thing that I want to throw in here, because I know you're going to have questions about it, and I may as well attack it once here. The difference between disjoint, so here I'll just kind of indicate that's the end of the example. Disjoint versus independent. Okay. So disjoint refers to the events. Can they happen at the same time? So disjoint, can they happen at the same time? Or maybe I'll say, can A and B happen at the same time? At the same time. If no, they are disjoint. Disjoint. And what does it mean to be disjoint? It means that the probability of A and B is 0. So that's a fact. If they're disjoint, then the probability of A and B is 0. For independence, does the probability of A, does the probability of A depend on the outcome of B? Right? If it does, then they are not independent, right? But I think that's kind of, it goes without saying. If they are, the probability of A and B must be the probability of A times the probability of B. both of these you have rely on the probability of A and B, right? Probability of A and B equals 0, or the probability of A and B is the probability of A times the probability of B. So if two events are independent, right? That means their probabilities are not kind of intertwined. Can they be disjoint? No, right? Because if they're disjoint, then the probability of A and B is 0, right? And then the only way to get 0 by multiplying is by multiplying by 0. So one of these would have to be 0, and then it just doesn't work, right? And so that's the difference, is that this one, so independence has to do with the probability, whereas disjoint means can they happen at the same time, right? So it's the outcome versus the probability. And that is where I will leave you. And that's probability. We're going to talk a lot more about probability, but in a different way. So we'll kind of leave this in the dust, so to speak. But you did it. Awesome. See you next time.